Hey, this is a lecture on the second half of Chapter 9, and it's on groundwater. Groundwater is water that's found in the ground, in the pore spaces and fractures and any little crevice beneath the surface, in the sediment, in the bedrock. And groundwater is a big part of the hydrosphere, at least the freshwater hydrosphere. It makes up 0.6% of the entire hydrosphere, but it's the largest reservoir of fresh water that's available to us humans. And here in Florida, the majority of our water use comes from our aquifer systems here. So groundwater makes up about 14% of all freshwater reservoirs. Most of that is glacial ice. But if we consider liquid freshwater reservoirs, meaning like not solid, like glacial ice, then groundwater makes up about 94% of all freshwater reservoirs. And you can see that here. So here is the share of total freshwater in terms of volume. 68% of that are in the ice sheets and glaciers. So that's in Antarctica and Greenland. So about 30% of that is groundwater. But if we break down, just all of the available liquid fresh water, 96% of that is groundwater. So it's a big reservoir. And geologically, it's important because groundwater is an erosional agent, very slowly, millimeters per year, but it can dissolve bedrock. And that's especially true in places where the bedrock is made of limestone. And when that occurs, you can form caves and you can also form sinkholes. You can see that in an image here. Sinkholes may form on the land surface as you dissolve away limestone. In addition to that, groundwater contributes some water to river systems, especially when in dry times. It helps contribute water to rivers so they continue flowing in drier periods. So they tend to equalize stream flow. So most groundwater soaks and becomes part of the groundwater reservoir through precipitation. And so if we think of the surface of the earth and we start kind of moving down beneath the surface, you'll initially run into the zone of soil moisture that's very close to the surface of the earth, and that is where you have water molecules sticking to soil particles. All right, that water is used by plants and typically evaporates back into the atmosphere and becomes part of the water vapor portion of the hydrological cycle. Water really isn't held in the zone, but if there's enough precipitation, it can percolate downwards into the unsaturated zone, what we call the vadose zone. That's the area just below the zone of soil moisture. And in this zone, the pore spaces include air and water. All right, so there's some pore space underneath the ground, very small. And then once kind of water percolates through the unsaturated zone, it'll hit an area where every single pore space is saturated with water. This is called the zone of saturation. It's also called the phreatic zone. The upper layer of the zone of saturation is the water table. Now I want you to imagine, like, say you got a shovel and just started digging out in your yard or just somewhere. You would initially be going through the zone of soil moisture, then going through the unsaturated or the vadose zone. But then eventually what you'll notice is that you'll start to get to areas that are wetter in the ground, or the soil will start to get moister. And then all of a sudden you'll get to a point where water just starts pooling. That's the groundwater. And the pooling water, or the surface of that pooling water, once you dig that hole deep enough, that's the water table. And above the water table is the capillary fringe. Okay, so here's a cross-section of what I've been talking about. Zone of soil moisture, the unsaturated zone where the pore spaces have water and air in them. Here's the water table, okay? And then below the water table is the zone of saturation. That's where the water is being held. Okay, so if you look at a cross section of a landscape, here's the water table, okay? And then below the water table is all the groundwater, all right? And the water table really mimics, like it's not a flat surface across a landscape. It kind of mimics the topography, kind of just in a subdued way. The capillary fringe above the water table is an area where water kind of fights the force of gravity upwards. It's kind of like, say you spill something on a counter and you use paper towel to clean it up. If you hold that paper towel over like the water, as the water soaks the paper towel, it'll kind of like rise upwards against the force of gravity, and that's what the capillary fringe is. Some of that water is kind of moving upwards into the unsaturated zone. Okay, if you notice here, there are two lines. There's normal water table and water table during drought. Yeah, the water table fluctuates. It fluctuates with precipitation. If there's more precipitation, then the water table will rise. And if there's less precipitation, the water table will fall. So the depth is variable. It varies in seasons and also wherever you're located. And so the shape of the water table, again, is not kind of like a flat surface, but it's kind of like a undulating surface that mimics the topography above it. Here in Florida, because we're so flat, we don't have a very steep gradient. The water table is quite flat. Okay. What you can do to imagine it, and it's a really good exercise, is if say you go to any Valencia campus and you look at any of the retention ponds or lakes, the surface of that water is roughly, if you can imagine that like surface of the water like cutting underneath the land surface, that's approximately where the water table would be. Okay. Here the book shows an example of a bunch of wells. Wells are holes bored into the ground. Modern wells have essentially they're like PVC pipes that have a diameter of like 3 or 4 inches, and they're kind of drilled into the ground past the water table, and they have kind of slits at the end of them, and then you can pump water out of it. And this is a good way to monitor the groundwater in different areas. Here, this is the state of Missouri, and here are the some monitoring wells all over the place. These are these blue dots that you see everywhere. And so these wells, see here's the water table, here's the well. This information in terms of the depth to the water table is sent to scientists at their office, so they can monitor how the water table is fluctuating up and down depending on precipitation. Here in Missouri, if you look at this graph over here, here's the actual data. So over here is time from July to March, and then on the y-axis is depth to the water table. So here in June, for example, the depth of the water table is 61 feet. So that means you'd have to dig 61 feet in the ground to reach the water, or to reach the groundwater. Here in Florida, it's very different. I worked for an environmental consulting company in South Florida, and we would look at wells. And in some places, especially in Miami, very close to the beach, let's say like Brickell, downtown Miami, the depth of the water table is only like 1.5 feet. So those areas are kind of prone to flooding. In other areas in Florida, it might be a little bit larger, maybe 10 feet, 6 feet, until you get to the water table. But that's very shallow, or a shallow water table. But anyways, here's Missouri. It's 61 feet till you get to the groundwater. But if you notice, there's a lot of dry weather, and then the water table falls all the way down to 66 feet. Okay, so that's a difference of about 5 feet in terms of drop of the local water table. But if you notice here, there are a bunch of rain events that occur in November, January, and April. And all that water, the rainwater, the precipitation recharged this groundwater system, and the water table rose back to kind of its original position at 61 feet below the surface. So that just shows you what contributes water to these underground reservoirs. And so some of the factors that influence how much water can be stored and how well that water can move, one factor is porosity. Porosity is a measure of the open pore spaces in a rock or sediment that holds the water. So it really depends on the size and shape of the sediment grains, how well they're sorted, how tightly packed they are, what type of rock it is. If it's a crystalline rock, there's only porosity through fractures. And porosity really determines how much groundwater can be stored. A good way to imagine this is imagine you have one of those like Home Depot orange buckets and you fill it up to the brim with golf balls, right? Golf balls are all kind of representative of sediment that would be packed together in a, say, sedimentary rock or something. Now, the bucket is full of golf balls and you can't fit anymore, right? But you can pour water in that bucket, right? Because the water is going to take up all the available space in between each one of those golf balls. That space is what the porosity is. Okay, so here's that example, or an example of it. And this is, the golf ball is kind of like a macro scale understanding of it, but when you're going down the sand-sized sediment, there's a lot of pore space in between each one of those sand grains. So this is what we're talking about. This is the water that's in between all this sediment. Okay. So if you have very well sorted sediment and very small sediment, you're not going to have a lot of porosity. But if you have kind of poorly sorted sediment in all different sizes, you could have a little better porosity here. But if you have larger sediment that are all well sorted, see here are some nice pockets of space for water to be in. Okay. Here's an example of like a kind of a thin section, cross section of a rock underground that has pore space, right? But if you notice, they're kind of by themselves. These pore spaces aren't connected. So the next kind of variable for groundwater systems is how well the water moves through the system, and that's called permeability. That's a measure of how well connected the pore spaces are. So here, in this example here, there's a lot of pore space. So this can hold a lot of water, but they're not well connected, meaning that this groundwater couldn't move very easily. Now down here, there's a lot of pore space, and all those pore spaces are very well connected, meaning that the groundwater can flow pretty easily through here. So this has high permeability. Okay, and so permeability is that ability of a material to transmit that groundwater. Okay, and so if you have good permeability and porosity, then what you have is an aquifer. And an aquifer is a permeable rock or sediment underground that is able to transmit and store groundwater freely. Now there are many materials underground that don't allow the transmission of groundwater, and we refer to those as aquitards. They're impermeable layers. A lot of times they're either sediment that's mostly made of clay or silt, or shale, or maybe some crystalline rocks. A lot of times those can prevent the movement of water. We call them aquitards. So aquifers, there are two types. There are unconfined and confined aquifers. Unconfined aquifers are where they can be recharged by superficial water. So if it rains, you see here, say it rains down, that water can infiltrate and then become part of this aquifer system, or add water freely to this aquifer system because the upper layers and the land surface is permeable. So it's a good and bad thing. It's a good thing because these aquifers can recharge fairly quickly with just kind of local weather and rain. But the drawback is that if there's any type of chemical spill, let's say there's a truck with some porta potty blue juices spill over off of 95 and crashes into a land surface and spills all that gross blue juice into the ground here, that can percolate down and pollute the aquifer, which isn't good. Okay, and if you drill a well into the aquifer, the water table aquifer is the same as what the water table would be at the well itself. Okay, so these aquifers are not pressurized. South Florida, there's superficial aquifers called the Biscayne Aquifer, and that's an unconfined aquifer. So South Florida meaning Miami, Fort Lauderdale, West Palm. In Central Florida, our aquifer is the Floridan Aquifer, and it's a semi-confined aquifer. And what a confined aquifer is where when you have an aquitard above and below an aquifer. So it's confined by two aquitards. Okay, so here's a cross section of that. Here's an aquitard above, and here's an aquitard below. Okay, and so these are confining layers above and below, which is a good and also not so great thing, because if it rains on the surface here, that water will not contribute or recharge the confined aquifer. But on the positive end, if there's if there's some contamination, a spill on this land surface, it won't contaminate your aquifer. It will remain, a pristine aquifer. A confined aquifer, if it's they can be pressurized, meaning that if you drill a well into it, the water will rise above the local confined aquifer water table. And the reason is because a lot of times these confined aquifers kind of pinch upwards towards the surface, and let's say somewhere at a higher elevation, here's the recharge area over here, and if it rains over here, that increase in elevation of the confined aquifer adds pressure to the remaining water, and that's what makes the water kind of come upwards. So a lot of confined aquifers, they can be pressurized. So groundwater moves, and it moves very slowly. It's not like when we talked about running water in rivers and how that turbulent flow. On average, groundwater moves about 4 centimeters per day. Okay, so that's approximately like 2 inches. And the idea of underground rivers, that is a very rare phenomenon. Most groundwater is kind of a slow, kind of creeping 4 centimeter on average per day moving groundwater. And the next slide has a good image of a simple groundwater flow system. And groundwater moves from higher areas to lower areas under the force of gravity. So areas where the water table is higher, that groundwater will move, quote unquote, downhill or down the water table to lower lying areas under that force of gravity. And in groundwater systems, areas where groundwater is replenished, we call those recharge areas. And when groundwater flows back to the surface of the earth, we call those discharge areas. So here's an example. We've got some rain up here in the hills. This would be a recharge area. So water will percolate downwards and hit the groundwater here. And notice that the water table here are at higher elevations. So the groundwater will move kind of under the force of gravity downhill. Okay, and then they move down towards the valleys in between these ridges. And in here would be considered a discharge area. Here we have a flowing river, and that groundwater will discharge into the river and equalize its flow. Here's a hypothetical groundwater flow system. Now, groundwater flow can be complex. Here they show you kind of 3 different levels of groundwater movement. There's in blue, all these blue areas are the superficial, near surface, local groundwater systems. Okay, so groundwater flows from higher elevations to kind of lower elevations. They can discharge in lakes and streams or a major river. But there's also deeper flow. So there's sub-regional systems that flow a little slower and deeper. Okay, and underground you can have a lot of different variables, different rock units. Some are permeable, some are impermeable. Here, this is representative of an aquitard, so groundwater kind of has to flow around this. And then here in black are the kind of deep regional systems of groundwater flow. All right, wells. Wells are holes bored into the ground beyond the zone of saturation. It's essential because typically people build wells to extract water, so you want to get past that water table. And they're very common. Maybe you have a well at your home. If you live beyond city limits or the limits of kind of municipal water, then typically you have a well for your everyday water use. And there are more than 16 million water wells in the United States, and 13 million of those belong to private households. So it's fairly common. And if you have your own well, you don't have to pay a water bill to a utility company. You could just be, sprinkling your lawn all day with your groundwater. But don't do that, because that's a problem. You don't want to waste water. If you draw out too much water from your well, that can cause a drawdown. And what that does is that lowers the local water table and creates a cone of depression. Okay, and that lowers the local water table so much so that you can actually run your well dry in some cases. Let's take an example here. We have two neighbors, right? This neighbor over here is, I don't know, John, okay, and he's got his regular sized well. And over here we have Karen. And Karen's built a new high capacity well, and she's growing, I don't know, a crop that requires a lot of water. I don't know, let's say kale. Karen and her kale. Okay, and so she built a high capacity well that draws up a lot of water to water up all that kale. Now what happens if she draws up too much water? See how this will lower the water table. Okay, it's kind of like if you drink your soft drink too quickly and then you drain it all and then all you have is ice left, right? So this is that cone of depression. So it lowers the water table, and now poor John can't pump out his water from his well. His well has run dry because of that lowering of the water table. That's when you use too much groundwater. There are artesian systems. This is where groundwater springs or discharges onto the land surface, or where if you build a well into a confined aquifer, sometimes water is under pressure in a confined aquifer and can actually shoot out of the well, so you don't have to pump the water out. Okay, but for that, in order for that phenomenon to happen, the water has to be in a confined aquifer and also an inclined aquifer. I'll show you what that means in a picture. So let's take a look. There are two types. There's a non-flowing artesian well, where the pressure from the groundwater it doesn't spill out of the well. It just kind of rises higher than the local water table. And then a flowing artesian well is where you have water just actively pouring out of the well you just built. Okay. Artesian systems can be, man-made if you build a well, but there are some natural artesian systems. Groundwater can reach the surface through fractures. We call those springs, and sometimes they're responsible for forming kind of desert oases. So water just having to spring in a low area, and that kind of creates life in a really dry desert. But here's your example of an artesian system. So here, this is your flowing artesian well here. So there's a well here and water just pouring out, okay? That's here. That's this example number 2. Okay, and the way this forms is here's your confined aquifer. Here's an aquitard above and below. Here's all the water in your confined aquifer, right? So over here, this is a low-lying area. Think of this as like Central Florida. Then over here is like North Florida, where there are some rolling hills. You're at a higher elevation. Okay, so what happens is the aquitard kind of pinches out as a unit and is exposed at the surface over here, and the reservoir rock is exposed at the surface, and this is a recharge area. So if it rains here, this is how this confined aquifer is recharged. Okay, and if you notice, it's at a higher elevation. If you draw a straight line from the water table here, you would be above the land surface when you're coming over to well 2 over here. So what happens is all this water is at a higher elevation. That provides a lot of pressure because this water wants to move down under the force of gravity, and that creates a pressure surface. So what happens if you build a well right here at site 2, you tap that confined aquifer, water will flow upwards to the pressure surface. If you go to well 1, if you build over here, let's zoom in over here, the water is still under pressure, but it will rise to the pressure surface, which is right here. So this would be an example of a non-flowing artesian well, and this one here would be an example of a flowing artesian well. One of the natural examples of an artesian system is in South Dakota. I think I have an image in the next slide where I'll show you that. But they can draw, it can have water move considerable distances. And then if you build in a certain area, in South Dakota, you can have flowing artesian systems. Here's an artificial one, or an example of one. A guy holding a funnel and then a tube to a low-lying area. An experience maybe you'll have at some point in college. You'll be creating an artesian system if you're at the end of this one, right? So all this fluid is under pressure because that is a higher elevation under the force of gravity. So your artesian wells will be forming on this side at a lower elevation. We do this on purpose too. We engineer, we create municipal water towers to create kind of artificial artesian systems. Okay. Here's that example in South Dakota. So this is a cross section from west to east across the Missouri River. So over here on the west side are the Black Hills. This is a recharge area, higher elevation. It rains here, and that water moves through the porous and permeable sandstones, Dakota sandstones. And so here's where a lot of water is stored. But on this end is a lower lying area, and there's a confining unit, a shale, that sits on top of that sandstone. So if you build wells down here, you'll have natural flowing artesian systems. Then here's your example of artificial systems here. The reason why we store water in water tanks way above ground is to create an artificial pressure surface, right? So that when you turn on your shower head or your faucet, the water's pressurized, right? It starts shooting out. And the reason is because we store water at a much higher elevation. So we do this, on purpose as well. All right, let's talk about springs. Spring is a natural outflow of water, and that's where the water table and ground surface intersect, and water just comes flowing out. And we have a lot of springs in Florida. In fact, I highly recommend doing that, taking some road trips to see some springs in central and kind of just the north of Orlando area. There are a lot of beautiful springs. I'm sure many of you are familiar with this. This is Aquifer Springs. All right, and literally groundwater just comes out of the ground and can create either a reservoir or a spring-fed river. Okay, here's another example just north of well north of Tampa, but this is Rainbow Springs. So the spring water just discharges from the ground, and then a river forms as a result. Okay, and if you've been to springs before, I'm pretty sure you'll notice that the water is very cold. Yeah, and that's because that water is coming from underground and then springs to the surface, and so it's a very nice cold water to get into in the summer. Some areas very pristine. There's Wakulla Springs and just south of the Tallahassee, which is real nice. Devil's Den. A lot of beautiful places you can visit in Florida where there are natural springs. Okay, so there are a lot of environmental issues surrounding groundwater. Groundwater is a resource, and it should be treated like one. So when we build wells, really you're kind of mining for groundwater, and there really isn't too much regulation on building wells and drawing out groundwater. In some places, or in many places, it doesn't rain as much as Florida, so groundwater systems don't recharge as quickly. One example is the High Plains Aquifer, and that underlies about 11 million acres in the Midwest, just north of West Texas and going further up north through Kansas. And that is one of the largest and most agriculturally significant aquifers That accounts for about 30% of all groundwater used for irrigation in the United States. So this is heavily used. Here's an image showing you those states: Nebraska, Kansas, Oklahoma, Texas, portions of New Mexico. And what's occurring here is that so much groundwater is being used from the high plains aquifer that the water tables are falling. And if you see areas colored in red, so areas in kind of south Kansas, west, northwest Texas, and Oklahoma, that is a drawdown of over 150 feet. Think about that, 150 feet. That is, the water table has fallen 15 basketball hoops stacked on top of each other. So yeah, that's major depletion of the groundwater resources there. And I mean, it kind of makes sense. I mean, West Texas is not a very, it's a very dry place. They rely on building wells and extracting water from the ground rather than use superficial water. There isn't much. So yeah, this causes a lot of drawdown, and that's a big problem. It's a big problem because what will happen is if you remove a lot of groundwater and the groundwater falls, it'll cause subsidence. And the ground surface will sink as a result of pumping water out. Think of the water, like the groundwater fills up all the pore spaces that were filled up with air. So it's kind of like a support. So if you kind of, slurp all that water out, that water is going to be replaced with air, and air is kind of more compressible, right? So if you start removing all the groundwater and the groundwater tables fall like 100 feet, for example, that means the surface of the land is also going to sink as a result of that. So some crazy examples of this are in the San Joaquin Valley in California, where a lot of alfalfa is grown. That's where they grow a lot of vegetables. A lot of farming is done there. But the subsidence has approached 9 meters. That's like 27 feet or 29 feet, around there. So the land surface has fallen 29 feet. So almost 3 basketball hoops stacked on top of each other. Other areas in the U.S. that are experiencing subsidence: Arizona, Las Vegas, New Orleans, Galveston, Houston. In Mexico City was built on a lake bed, and some of the earliest buildings that were constructed, there's been as much as 7 meters of subsidence, and the entrance to some of those old buildings are now at the 2nd floor, and they have a basement built in already, which is the 1st floor. Here's your San Joaquin Valley example. So that's this area here in Central California, in the valley. Okay, so in 1925, this is where the land surface was, and then today, this is where the land surface is now. So over 52 years of heavy groundwater pumping, that has lowered the water table approximately 30 feet in 50 years, which is incredible. Plus, you can have collapses that occur as a result of groundwater depletion. Okay, another environmental issue, and this is particularly true in coastal regions, is saltwater intrusion. So South Florida, Miami, Fort Lauderdale, West Palm Beach, they have to deal with this. And this is, if you excessively withdraw a lot of water, that can cause salt water to be pulled inland and can be drawn into those wells and contaminate that freshwater supply. And once a well has saltwater intrusion or pulls up salt water, it's a ruined well and you can't use it anymore. Freshwater is less dense than saltwater, so it kind of floats on top of the salt water. So let me just show you a cross-section image of this. So here's an example. Here's your coastline. Here's your freshwater cap sitting on top of the salt water, right? So if you live here and you have a well, you start pumping out the water. If you pull out too much water, then you're just going to start creating a situation where salty groundwater moves inland and can contaminate your well, and then that kind of ruins the groundwater resource here. In South Florida, if you build a well anywhere east of I-95, you're going to get salt water. So all the well fields in South Florida are way out west, like in Plantation, closer to the Everglades, because they want to avoid the saltwater contamination. If you live in places that are have really cold winters, where ice is very common, they'll throw salt on streets and sidewalks And that can be a potential contaminant because that washes away into these like recharge basins, and that can contribute to the contamination of the water table below. Another really common environmental issue is just contamination. The primary source or a very common source of groundwater contamination is sewage. Okay, that those are, could be leaks from our local plumbing, or it could be like a lot of people who live beyond city limits have septic tanks, and septic tanks can leak, and that sewage, raw sewage, can leak into the groundwater system. But sewage can be purified if it's underground long enough in slow-moving aquifers. Here's a dramatic example of oil spilling on the ground. That can also be a contaminant to groundwater systems. But if you have a very fast-moving groundwater system that where it takes kind of days or weeks for water to flow through, here's your example. We'll use Karen and John again. So John this time, goes to eat at Taco Bell, right? He's here, and he creates some Taco Bell water, and that goes into the septic tank. But his septic tank's leaky, and that leaky Taco Bell water, that contaminated water is kind of going through this cavernous limestone pretty quickly. And then when Karen's brushing her teeth, her well is going to pull up that contaminated water, and she's going to be brushing her teeth with Taco Bell water, which is terrible. And this is a bad spot to build a well. You should know the direction of groundwater flow if you were drawing from wells, and then place your well somewhere where it won't be near someone else's septic tank, or at least down flow. Okay, but in other situations it doesn't even matter with the groundwater flow, because if it takes months or years in a slow moving groundwater system, sewage eventually gets purified, because there's a lot of microbes and bacteria in the ground and in the groundwater system that will kind of clear out the waste and use up the nutrients in that waste and purify the water. So in this situation, situation B, Karen can freely brush her teeth in that water and not have to worry about Taco Bell contamination. Some crazy issues with groundwater contamination can result from the creation of cones of depression. Remember, if you overdraw the groundwater, it can actually it can reverse the direction of groundwater flow. So you could have been smart and build a well in a location where you're like, okay, there's a landfill over here and the groundwater's flowing in this direction, so I'm going to build a well over here to avoid any possible contamination from the landfill, right? You don't want trash juice coming up in your well, right? So what the problem is that if you have a well and you start overdrawing that area, you can actually change the direction of groundwater flow by altering the water table. So that can lead to some problems. But other major sources of contamination include fertilizers, pesticides, chemicals, industrial materials. When you go to gas stations, those big fiberglass tanks underground are usual suspects for contamination. And also dry cleaners, right? Dry cleaners, how do they clean your suit without using water? They got to use chemicals, right? Or a fingernail. I don't know how they do it. But anyways, they use chemicals. And sometimes those dry cleaner places just pour those chemicals out, into the ground. So, yeah, those are some possible contamination. So here, landfills are an area where you could have some landfill juice going into the groundwater. Here are some, either a septic tank. Sometimes when you go to gas stations, well, here in Florida, all the gas stations have huge fiberglass tanks underneath the ground, and those are huge sources of contamination. And gas is a carcinogen, so groundwater does a lot of work, and it dissolves rock, especially limestone. Most groundwater is just slightly acidic. It contains carbonic acid, and the reason why it has carbonic acid is because when you have precipitation, that water will interact with atmospheric carbon dioxide, and also pick up some of that from decaying plants as it travels or percolates through the ground. And that carbonic acid will react with limestone and start dissolving it away. Okay. And so what happens with that is that's what creates caverns. Those are the spectacular results of thousands of years of erosion via groundwater. Most of those caverns are created by acidic groundwater dissolving soluble rock. So there are over 17,000 caves that have been discovered in the United States. We have some in Florida, Gainesville. There's some caves there, and in Tallahassee there's some caves, but a lot of those caves are kind of under the groundwater level. The most famous examples of impressive caves are Mammoth Cave in Kentucky, which is like, I think there's over 400 miles of cave passages there, which is incredible. About 12 miles is open to the public. So you can go underground and explore about 12 miles of caves at that national park, which is incredible. Pictured here in this slide, what you're looking at, that's Carlsbad Caverns in New Mexico. And this one's pretty impressive. You can take an elevator down to the main kind of cathedral-like room, which is 1,500 feet underground, which is impressive. And that's in New Mexico. Here's the entrance to Mammoth Cave in Kentucky. So the way these caverns develop is that acidic groundwater kind of slowly dissolves the limestone, kind of millimeter per millimeter, every year. And so over the course of thousands of years, then they'll create huge void space and create these caverns. And they'll also form dripstones. Dripstones are where kind of water percolates through these void areas, like water percolates through the vadose area, and as it goes down, it'll precipitate a little calcium carbonate at the end of the droplet, and it'll create speleothems. Okay, and this is that's a general name for all dripstone features, but stalactites hang from ceilings, and stalagmites grow from the floor of the cavern, and sometimes they join together and form a column. Let's see if I got a picture. Okay, so here are stalactites, stalagmites, and then here is a column. I don't know why I said that twice. That was weird. Okay. And landscapes that are kind of contain a lot of limestone bedrock, we refer to that as karst topography, or a landscape that's been kind of created through the dissolving power of groundwater. We refer to as karst topography. And so the common features of these areas are kind of irregular terrain, sinkholes will form, and sinkholes are essentially when limestone dissolves away beneath the surface, and it forms kind of an arch, and then there's a collapse. So they can be kind of dangerous. Sinking streams, so streams can just disappear into the ground. And then also tower karst, which I'll show you a picture of pretty soon. Okay, so here are the areas that are have limestone as bedrock in the United States. You can see vast areas in and around, so near like Tennessee and Kentucky, where Mammoth Cave is. All right, look at Florida. It's all green. Our bedrock is limestone, so a lot of those features of karst topography we'll find here. And this is how carbonic acid forms. So here's CO2, here's precipitation, and that carries carbonic acid. And then carbonic acid reacts with limestone to create material that's in solution, and so it dissolves away limestone. And so over time, karst landscape will evolve in this direction. So if you go to Mammoth Cave in Kentucky, this is what the landscape looks like over a long period of time of this type of development. So you'll have sinkholes forming, perfectly circular sinkholes. It's a general feature of sinkholes that form with those collapses. Springs kind of shooting out of these areas here. There's a river, caverns, sinking streams that disappear. That's very typical of a karst landscape. Okay, here are some sinkholes in New Zealand, okay, that have formed via that collapse. This is one that has occurred in Lake City, Florida. This house has a new pool. All right, this is quite dangerous. I mean, people fall in there. Some people have died from sinkholes kind of destroying your home. You can buy sinkhole insurance for your house if your area is prone to it. But in Florida, typically what will happen is sinkholes form all the time in limestone bedrock, but the dangerous ones form if you have overburden that's has some clay in it, because that'll keep that material kind of stuck together, so that when that void forms, it just thins and thins out, and then there's a major collapse. If your overburden is mostly sand, the sand will kind of sink and fill in the void in the limestone, and then you'll just have a low-lying area. And this, typically in Florida, this becomes a swamp or a lake, or a low-lying area that that's prone to flooding, and that's because of the dissolution of limestone below. But in areas where there's a lot of clay, you won't notice that there's limestone dissolving beneath the ground until there's a collapse, and then this fills up to become a new lake. There's another example of a sinkhole. Look how perfectly circular that is. That is incredibly unlucky. I feel real sad. This is someone's house, and it just was devoured by the sinkhole. And there's no warning, really. If you notice their next door neighbors, yeah, they've got a moving truck. They're getting out of there. Okay, here is this is from the Florida Geological Survey. This is the kind of sinkhole-prone areas. Okay, I'm sure most of you either live in Osceola, Polk, or Orange County. So we're kind of in this region. So we're in the orange, highly sinkhole-prone, to red, very high sink-prone. There's a lot of sinkholes that occur in Polk County. A bunch of them have been in the news. Go ahead and Google fertilizer plant sinkhole. That's a very interesting read. But a lot of sinkholes actually form in Pasco and Hillsborough County. Human activities kind of exacerbate the formation of sinkholes, and I'll explain why. But yeah, South Florida, you don't really see that many sinkholes, and the reason is because the water table is so high there, kind of supports the land above it. So that's one reason, amongst others. But sinkholes are triggered by loading on the surface. So if there's a lot of buildings, large buildings, adding a lot of weight, that can cause a sinkhole. Over pumping. Remember, if you lower the water table, here's your example. So this is a land area. Here's the normal water table, right? Somebody built a pumping well, and they lowered the water table. Here's that cone of depression. So if you lower the water table, it kind of lowers the support of the local area, and then you'll have sinkhole formations here and here, okay? Or if there's long-term drought, which can happen in Florida. If there's long-term drought, that'll cause the water tables to fall, and then sinkholes will form as a result. Some signs of sinkhole formation: if you have slumping cracks or structures in your home, things that are like cracks in your foundation of your wall, like that are thicker than, let's say, a credit card you can fit it through, that's a warning sign that there could be some slumping or the formation of a sinkhole. If you have ponding rainfall in a certain area, that could be kind of weird. Sediment in your nearby well could be an indication. Or like if you open up a door in your house and it just swings wildly open, that's because perhaps it's, the whole frame is tilted. Those are worrying signs that there could be a sinkhole forming in your area. Okay. So sinkholes or dissolution is most likely to occur in areas where there's a lot of recharge and unconfined aquifers. Okay, and again, sinkholes, they're accelerated by our activity. What we do is we increase and focus the runoff. We create a lot of surfaces that are impenetrable, so like roads, houses, sidewalks. When it rains on that stuff, that water's, instead of infiltrating into the ground, it's going to run off into like directed areas and into low-lying areas. So it increases runoff into certain areas, which can flood them or increases the recharge in those areas. And we artificially lower the water table by pumping a lot. Here's an image of Pasco County and Hillsborough County. Here are all the sinkholes from 1960 to 1991, and the well fields are square. Well fields are areas where we pump out water for municipal use. So if you notice, a lot of the well fields are here and over here. And if you notice, around the well fields, you'll have boom, 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 all these sinkholes form. And that's largely because those well fields lower the local water table, and then sinkholes form as a result. Okay, and they typically form this kind of perpendicular, circular kind of sinkhole. This one was in downtown Guatemala City, Guatemala. Surprisingly, nobody died during this sinkhole. There is an end to this abyss, but that's another example of a sinkhole that formed. If you go to like Google Maps and look at a kind of a map of Florida, look at all the circular lakes that you find in Central Florida. Those are all former sinkholes. There was either a collapse or maybe there wasn't a collapse, it just created a depression. But those circular lakes are former sinkholes. Another feature of karst topography are these beautiful tower karsts that will form. We find a lot of these in Southeast Asia. And that's because there's preferential dissolution in certain areas, and then it leaves behind these kind of huge towers, which are very striking and beautiful.